Welcome to Programming Fluency. This is section 4.4, Recursion. So far, one function has called another function, but nothing says the function being called has to be a different function. In this video, we ask a surprising question. What happens when a function calls itself? Let's begin. So far, one function has called another function, but nothing says the function being called has to be a different function. We ask a surprising question. What happens when a function calls itself? The answer is one of the most important ideas in computer science. It is called recursion. This is the plan for this video. First, we meet the surprising idea, a function that calls itself. You will see that it also needs a stopping condition, or it would never end. Next, we name the two essential parts every recursive function must have: the base case, which stops the recursion, and the recursive case, which does the calling. Then we look at the call stack. This is where paused calls wait, as the stack winds up with each new call and unwinds as each call finishes. After that, we see what goes wrong when the base case is never reached. The stack keeps growing until it runs out of room. That is called stack overflow. Finally, you get a reliable pattern for writing recursion, and we compare recursion to solving the same problem with a plain loop. A function can call another function, but nothing stops a function from calling itself. Look at this function named forever. It prints hello, then it calls forever again. That second call prints hello and calls forever a third time, and again, and again. It never stops on its own. It stops only when the program crashes. We will see exactly why later in this video. Now, if you add a stopping condition, a way for the function to not call itself in certain cases, something powerful appears. You get a function that solves a problem by breaking it into a smaller version of the same problem. It solves that smaller version, and then it combines the results. This is called recursion. Recursion is a technique where a function calls itself to solve a problem by breaking it into smaller instances of the same problem. Let's meet our first recursive function, factorial. The factorial of n is the product of all positive integers up to n. Look closely. 5 factorial equals 5 times 4 factorial. 4 factorial equals 4 times 3 factorial. Each factorial is defined in terms of a smaller factorial. But the chain has to stop somewhere. It stops at 0 factorial, which equals 1 by mathematical convention. This self-referential definition, with a stopping value and a smaller step, is the essence of recursion. The mathematical definition translates directly into C. The if statement checks whether n equals 0. If it does, the function returns 1, with no further calls. Otherwise, the function returns n times factorial of n minus 1. So factorial of 5 calls factorial of 4, which calls factorial of 3, and so on, all the way down to factorial of 0. Factorial of 0 returns 1 without calling itself again. That single return value flows back up the chain. Every recursive function has two essential parts. First, the base case. That is the condition where the function returns a result without calling itself. In factorial, the base case is n equals 0, which returns 1. Without a base case, the recursion never stops. Second, the recursive case. That is the part where the function calls itself with a smaller argument, n minus 1. The smaller argument moves the problem closer to the base case. The function must make progress on every single call. So where does C keep track of all these paused calls? When factorial of 3 runs, it has to wait for factorial of 2, which waits for factorial of 1, which waits for factorial of 0. 4 calls, all paused at once. The answer is the call stack. The call stack is a region of memory that tracks active function calls. Every time a function is called, C pushes a new stack frame. Each frame holds that call's parameters, its local variables, and a return address, which is where in the calling code to resume. When a function returns, its frame is popped off. Last in, first out. The most recent call sits on top. Let's watch the call stack for factorial of 3. It starts with main's frame at the bottom. Main has called factorial of 3, and now it waits for the result. First the stack winds up. Factorial of 3 is pushed on top of main. It cannot finish yet because it is waiting for factorial of 2. Factorial of 2 is pushed next. It is waiting for factorial of 1. Factorial of 1 is pushed on top. It is waiting for factorial of 0. Now factorial of 0 is pushed. This is the base case. It returns 1 right away with no more calls. The stack has finished winding up. Now the stack unwinds. Factorial of 0 returns 1 and its frame is popped off. Factorial of 1 takes that 1, computes 1 times 1, which is 1, and returns 1. Factorial of 2 computes 2 times 1, which is 2, and returns 2. Factorial of 3 computes 3 times 2, which is 6, and returns 6. Main receives 6. The stack grew on the way down and shrank on the way back up. This is the same trace as a table. Read top to bottom for the winding phase, then the resumes for the unwinding phase. Factorial of 3 waits, computing 3 times factorial of 2. Factorial of 2 waits, computing 2 times factorial of 1. Factorial of 1 waits, computing 1 times factorial of 0. Factorial of 0 hits the base case and returns 1. Now the unwinding begins. Factorial of 1 computes 1 times 1 and returns 1. Factorial of 2 computes 2 times 1 and returns 2. Factorial of 3 computes 3 times 2 and returns 6. Each row is 1 moment in the life of the call stack. This is something critical. Each call has its own copy of n. Factorial of 3 has n equal to 3. Factorial of 2 has n equal to 2. These are separate local variables, living in separate stack frames. Because each call gets its own frame, the recursive calls do not overwrite each other's, and this is exactly the pass by value rule and the local scope rule you learned earlier. Every call is independent, and that is what makes recursion work correctly. Now remember the forever function from the start. Let's see why it crashes. The call stack has a finite size. On most systems, that is only a few megabytes. Every function call adds a frame, and every frame uses memory. If a recursive function never reaches its base case, it keeps pushing frames until the stack runs out of space. The result is a stack overflow. A stack overflow is a runtime error that happens when the call stack exceeds its allocated size. The operating system then terminates the program, often with the message segmentation fault. Missing the base case is not the only danger. A base case that exists but is never reached is just as fatal. Look at bad factorial. It has a base case, n equals 0, but watch what happens if you call it with a negative number. Bad factorial of -1 calls bad factorial of -2, then -3. It subtracts 1 every time, moving further from 0, not closer. The base case is never reached and you get a stack overflow. The fix is simple. Use if n is less than or equal to 0. Now negative stop 2. Every recursive function follows the same 4-step pattern. Step 1. Identify the base case. What is the simplest input, and what should the function return with no computation? Step 2. Identify the recursive case. How do you break the problem into a smaller version of itself? Step 3. Ensure progress. Each call must move closer to the base case, or the recursion will never end. Step 4. Combine. How does this call use the result of the smaller call to build its own answer? Follow these 4 steps, and any recursive function becomes straightforward. Let's apply the 4 steps to a new problem. Summing the integers from 1 to n. Step 1, the base case. Sum of 0 is 0. Step 2, the recursive case. Sum of n is n plus sum of n minus 1. Step 3, progress. Each call reduces n by 1. Step 4, combine. Add n to the result of the smaller call. When you call sum of 5, it unwinds to 5 plus 4 plus 3 plus 2 plus 1 plus 0, which is 15. Each call adds just one number and delegates the rest to the smaller call. Not every recursive function returns a value. A void function communicates by printing through side effects, and here is a subtle point. Where you put the recursive call changes the order of the output. On the left, countdown prints the number before the recursive call. That gives descending output. 3, 2, 1, go. On the right, count up recurses first, then prints after. That gives ascending output. Start 1, 2, 3. Same structure, opposite order. What changes is when each call does its work. Recursion and iteration are equally powerful. Most recursive functions can be rewritten as a simple loop, and any loop as recursion. So when do you choose each one? Look at the trade-offs. For clarity, recursion often mirrors the mathematical definition, while iteration needs an accumulator pattern. For memory, each recursive call uses a stack frame, while a loop uses constant memory, just one frame. For stack risk, deep recursion can overflow, while a loop has no stack risk. And recursion is best for problems with a naturally recursive structure, while loops are best for simple counting and accumulation. Let's look at the most common recursion bug, a missing base case. In this code, sum just returns n plus sum of n minus 1. There is no if statement, no stopping condition, so it calls itself forever until the stack is exhausted. The result is a stack overflow. The fix is to add a base case. Put if n is less than or equal to 0, return 0 before the recursive line. Now the recursion has somewhere to stop. This is a second common mistake, a recursive case that does not make progress. This function has a base case n equals 0, but look at the recursive call. It calls broken of n, not broken of n minus 1. The argument never changes. So broken of 5 calls broken of 5, which calls broken of 5 forever. The base case is never reached and you get a stack overflow. The fix is to shrink the argument. Call broken of n minus 1, so n decreases by 1 every time. Let's recap. Recursion is a function calling itself to solve a smaller instance of the same problem. Every recursive function needs a base case, which stops the recursion, and a recursive case, which shrinks the problem. The recursive case must make progress toward the base case on every call. The call stack gives each call its own frame, with independent copies of n, which is why the calls do not interfere. Without a reachable base case, frames pile up until a stack overflow crashes the program. And remember, use recursion when the problem is naturally recursive, and use loops for flat counting. Next, in Chapter 5, you will move from single values to collections. You will learn arrays, which store sequences of same type values, and strings, which are character arrays with a special termination convention.